Morning, everybody. Here is FRQ number 1 from the 2009 test. So let's just dive in and get solving here. In this question, we've got a 3 kilogram object moving along the x-axis in a region where the potential energy is a function of x given by u of x equals 4x squared. We're using joules, x is in meters. And when the object passes the point x equals negative 0.5, its velocity is 2 meters per second. And all of the forces acting on the object are conservative. So this statement right here is important because this is going to tell us that we don't have any non-conservative forces there. Therefore, the total energy in the system is going to remain constant the entire time. All right, so that's helpful to us. Let's dive in on letter A here. Calculate the total mechanical energy of the object. All right, so we've got this thing moving in the x world, back and forth. And it's got potential energy and it has kinetic energy. Therefore, our total mechanical energy is just simply going to be the total amount of kinetic energy and the total amount of potential energy. So we can say that energy is equal to the spring energy plus the kinetic energy. All right. We have expressions for both of these. The spring energy was given to us in an equation as 4.0 x squared. Kinetic energy is 1/2 mv squared. And if we look at this question, it says the total mechanical energy of the object. Now, if all of the forces are conservative, we know that at any point along this motion, the total energy is going to be the same. So let's just look at what's given to us. When the object passes x, its velocity, x equals negative 0.5, its velocity is 2. So let's just plug these numbers in. So energy is going to be equal to 4.0 x squared, and x here is going to be negative 0.5 meters squared plus 1/2 times the mass, which was 3 kilograms, times v squared, which is just 2 squared. When we solve that out, we're going to get that the total mechanical energy in this system is 7.0 joules. All right. Points on this one. 1 point for adding together the energies and 1 point for the correct answer. All right. Moving on to letter B. Calculate the x-coordinate of any points at which the object has 0 kinetic energy. All right. So this was part A. Let's move on to part B. Calculate the x-coordinate of any points at which the object has a 0 kinetic energy. All right, so here's what we can say here. Where the object has a 0 kinetic energy, all of its energy has to be potential because this statement right here has to hold true the entire time. Energy is equal to the kinetic plus the potential energy of the spring. Therefore, if the kinetic energy is 0, all of the energy is the potential energy in the spring. So we can substitute our equations here. This is 4.0 x squared. Now I just figured out that the total energy in my system is 7 joules. So this is 7.0 joules is equal to 4.0 x squared. Now we just solve for x. Divide by 4.0. And then I take the square root. So this is going to be 7.0 divided by 4.0 square root is equal to x. And that means that our x value is going to be equal to plus or minus 1.3 meters. At either negative or positive 1.3 meters, we're going to have a kinetic energy of 0. Points on this one. We get this point for recognizing that all of the energy is potential energy of the spring. We get 1 point for substituting your answer from part A, and we get 1 point for including the plus or minus here. It's all attached to the plus or minus, all right? So there's A and B. Let's go to part C. Part C says calculate the magnitude of the momentum of the object at x equals 0.6 meters. All right, calculate the momentum. So let's think about what we know here. We know what the position is. We do not know the velocity, and we know that in order to solve for momentum, I need the velocity. So I need to first figure out what my velocity at 0.6 meters is. I'm going to do that using energy, all right? So start off with our statement again. Energy is equal to kinetic plus the potential energy of the spring. Now let's think about this. I know what the total energy is. It's 7 joules. I know what the potential energy in the spring here is because I can solve for it. So if I do this, this is going to be 1/2 mv squared plus 4.0 x squared. I know E, I know M, I know X. Let's plug in and solve. So this is going to be E minus 4.0 x squared. All right, all of this is going to be multiplied by 2 divided by mass with the square root of that whole thing taken to equal V. And now we can plug in. So this is going to be 2 times 7.0 joules minus 4.0 times our position, which was 0.6 meters squared, divided by the mass, which was 3.0 kilograms. Square root of that whole thing equals V. And when we solve this out, guys, we're going to get that V is equal to 1.92 meters per second. All right, that's step 1 here. We still have a ways to go. Now we can calculate the momentum at that point. So we know that momentum is equal to mass times velocity. So this is 3.0 kilograms times 1.92 meters per second, which means that the momentum at this point is going to be equal to 5.0 kilograms times meters per second. Okay. Now let's look at where the points here came from. We get 1 point for, again, recognizing that this is the total energy. Okay. We get another point for using this equation for kinetic energy. All right. And we get 1 point for substituting the correct value of velocity into that equation right there. All right. So there's part C. There's our momentum. Moving on to part D. Part D is asking us, calculate the magnitude of the acceleration of the object as it passes 0.6 meters. Okay, so a few ways that we could do this here. I'm going to highlight the way that I think is the most straightforward. So looking at part D, we need to figure out the acceleration. Now, what we need to remember here is that acceleration and force are deeply connected. And the one statement that we should definitely recall here is that force is equal to the negative of the derivative of the potential energy. Okay? This would be a statement, guys, that I would include on your reference sheet, on your little cheat sheet, okay? Because that's something that's not on the regular equation sheet, and it's something that is really, really easy to forget. So this is what's really going to help us here, because I have an expression for the potential energy. So this is going to be negative derivative of d dx of 4.0 x squared. Well, I can take the derivative of 4.0 squared. This is going to be the force is equal to negative 8.0 x. All right. Now, I know that force is equal to mass times acceleration. So mass times acceleration is equal to negative 8.0 x, which means that acceleration is equal to negative 8.0 x divided by mass. Now I just plug in. So this is negative 8.0 times 0.6 meters divided by 3.0 kilograms. And what I'm going to get is that the acceleration at this point is going to be equal to negative 1.6 meters per second squared. All right, points on this one. Points on this one come from recognition of this relationship, recognition of plugging that relationship in, and then using the correct value for the force to get the acceleration. All right, so there's parts A through D. Now let's move on to the final part where we graph everything. Don't want that there. So part E tells us on these axes below, sketch the graphs of the object's position, x versus time, and the kinetic energy versus time. And assuming that x is equal to 0 at time equal to 0, the two graphs should cover the same time interval and use the same scale. Okay, so we know that at x equals 0, time is equal to 0. So let's just start there. I know I'm going to have a point right here. Now this thing is oscillating back and forth, which means it's going to have a maximum x value and a minimum x value that it oscillates in between. Now this thing is also going to have a maximum velocity. Think about when it returns back to its original starting point, which means it can have a maximum kinetic energy. Okay? Now something that we learned about oscillations, and I know that oscillations aren't going to be on this test, but it's still a worthwhile conversation to have, is that if I have something on a spring and it's moving back and forth, there are some extremes on this. We have the extremes for the x values. Here's the negative x, here's the positive x, here's equilibrium. And we know that at these extremes for positive and negative x, all of my energy is in the spring. We know that at equilibrium, all of my energy is in kinetic energy. This helps us because when kinetic energy is at a maximum, potential energy is at a minimum. Potential energy is associated with the position. Therefore, if the position is at 0 at time equal to 0, that means that my kinetic energy is at a maximum. All right? And the relationship between these is just going to be a relationship that looks something like this. It's pretty good. So, when position is at a maximum, kinetic energy is at a minimum. Again, when position is at a maximum, kinetic energy is at a minimum. When position is at 0, kinetic energy is at a maximum, and so on, and so on, and so on. All right? So if we connect the dots for kinetic energy, oh boy, that was not good. I'm going to redraw that one. Here we go. Something like that. It's a terrible, terrible cosine graph, but you get the point. All right. Those are the relationships. Looking at the points here. All right. You get 1 point for recognizing that this should be a full sine curve. All right. 1 point for recognizing that this should be a full cosine curve. And then 1 point for matching these maxes and mins. All right. That's it, guys. Let me know if you have any more questions on 2009 FRQ number 1.